Welcome to the first week of a 7-week mini-series on the dangers of containment seals. Each week we will discuss a different topic relating to all aspects of containment seals, their application and design. This week covers the history of containment seals and how they came to market. The display graphic is of a single mechanical seal. These devices were originally brought to market by George J. Cook in 1923 and was originally known or referred to as the end face seal. As such, they are very much well understood devices, being an invention of over 100 years old. Contrary to belief, all mechanical seals leak to some extent. On liquids which condense, this leakage can be seen in physical droplets, but other process fluids which can vaporize at atmospheric pressure will form vapor leakage, and this is referred to as emissions. If the process media is hazardous, toxic, etc., legislative and environmental requirements are increasingly calling for this to be contained, preventing any leakage to atmosphere. This has become more prevalent in recent years as we understand more about emissions and how we protect the environment and our population. Predating API 682, most operators used a tandem seal, which was often two component seals orientated in the same direction, in series, with a lubricating fluid between the two seals. API 682 now officially refers to this as an Arrangement 2, Plan 52, and a demonstration of its operation will play in this short video. The definition being that the buffer fluid between the inboard and outboard seal faces is at a lower pressure than the process pressure. The tandem seal offered a unique set of advantages, including improved safety, increased reliability and reduced maintenance requirements, but was not without its drawbacks. Arrangement 2 seals still let process liquids leak from the primary seal, but catch it to allow it to be vented or disposed of more safely than a single seal. Containment seals came to the market in the late 1990s, and the application of them increased steadily for many years as plant operators demanded better leakage control without the additional cost and complexity of liquid buffer and barrier systems. They in particular grew in popularity on light hydrocarbon processes where operators struggled to meet an ever-increasing level of emission reduction brought in by regulatory compliance, safety aspects, and environmental controls. They were officially recognised in API 682 second edition in 2002, but prior to this, there was no recognised piping plans or strategies for operating them successfully. Operators devised their own methods to suit themselves, and it was the Wild West in terms of piping plans. Some operators simply connected them to a drain pipe with a pressure switch and sometimes even just a gauge for a visual indication of the seal's performance. These different methods and the pitfalls will be discussed in the coming weeks. API 682 first edition came around in 1994 and officially termed the tandem seal Arrangement 2. It merely stated it recommended it to be connected to a flare, but all too often in the field it wasn't, or was connected to the suction of the pump via a non-return valve. At least second edition now dictates that it should be connected to flare, making this connection mandatory for successful performance. The second edition also now recognised the existence of containment seals and expanded the piping plans to support them. These namely being Plans 71, 72, 75 and 76, which will be elaborated on later in this week's video. The containment seal is termed an Arrangement 2 seal, i.e. still letting liquids or vapours escape from the machine into the seal interspace, but dealing with the leakage in a safer and more reliable manner. According to API 682, current 4th edition, containment seals are designed to operate in normal running conditions of up to 0.7 bar or approximately 10 pounds per square inch. In the event of a primary seal failure, the containment seal will be capable of sealing the seal chamber conditions for a minimum of 8 hours at full seal chamber pressure. The highlighted section here in yellow is the part that AESSEAL disagrees with. We are of the opinion that all containment seals should be run with a Plan 72, in conjunction with an additional containment seal plan, either Plan 75 or 76. It's also important to note that containment seal designs can either be contacting or non-contacting, and this does present differences in performance. As previously stated, piping plans should be combinations used in unison. For example, Plan 72 and 75 or Plan 72 and 76. In other words, the only choice really is to use 75 or 76, with the Plan 72 being mandatory. 72 is never used in isolation, but the market misunderstood this, and operators on a regular basis just supported containment seals, often with nothing. In essence, they simply adopted the Plan 75 or 76. They did not choose to adopt the Plan 72, which is the gas buffer, which we believe is unsafe practice. You have to ask yourself the question, why did they do this? My professional response to this would be a number of reasons, but specifically cost, and to reduce complexity. However, in their defence, API 682 did not state Plan 72 had to be used in unison with Plan 75 or 76, and this is where the confusion creeps in. This animation illustrates a dual containment seal for vaporizing leakage. The inner seal is lubricated by process fluid and is often cooled via a suitably sized Plan 11 flush recirculation line. With all the gland ports plugged, Plan 71, the normal working leakage from the inner seal will fill the containment seal cavity and eventually pressurize this cavity. This will then leak past the containment seal and out to atmosphere. Leakage will potentially damage the contacting containment seal. Remember, they are dry containment seals designed to run dry with a buffer gas. A non-contacting containment seal design will simply allow leakage to flow to atmosphere. With normal leakage that is vaporizing, gas emission leakage, the seal should be connected to a flare or vapor recovery system, which is termed Plan 76. The vapor flows to flare via an orifice. Back pressure is monitored by instrumentation. An increase in back pressure will strongly indicate potential inner seal failure. There will be some leakage from the containment seal cavity to atmosphere, more so with non-contacting containment seals due to a wider sealing gap. The introduction of an inert gas, usually nitrogen, into the containment seal cavity, which is the Plan 72, is used to try and sweep any leakage from the cavity before it damages the containment seal. The Plan 72 also prevents normal leakage of the process to atmosphere, as any leakage will be inert gas. This also offers a level of cooling to the containment seal assembly, like the Plan 11 does to the inboard seal faces. The AESSEAL recommendation and accepted best practice is always to use a Plan 72 in conjunction with Plan 76. Frequently, AESSEAL have found that containment seals has been applied without the appropriate piping plan for the service. And in our opinion, this can be dangerous, as you have a hydrocarbon vapor mix and seal faces which generate heat, especially contacting containment seal designs. This animation again illustrates a dual containment seal, but this time for condensing leakage. Again, the inner seal is lubricated by process fluid and cooled via a suitably sized Plan 11 flush recirculation line, but on condensing fluids, this could also easily be a Plan 03 to provide sufficient cooling to the inboard seal. With all the gland ports plugged, Plan 71, the normal leakage from the inner seal will fill the containment seal cavity with fluid and pressurize the cavity. This will then leak past the containment seal and out to atmosphere. Leakage will damage the containment seal. Remember, they are dry containment seals designed to run dry, but then on process fluid for only 8 hours. With normal leakage that is condensing, the seal should be connected to a leakage collection vessel, which is termed a Plan 75. The collection vessel collects the accumulated drips, and the level is monitored by instrumentation. When the leakage collection system indicates it is full, it requires to be drained down, which is potentially to the plant open, closed drain system, depending on how hazardous the leakage is. As it's common for the process fluid to have some entrained gas phase components, the collection vessel is connected to the plant flare system as well. There will be some leakage from the containment seal cavity to atmosphere, more so with non-contacting containment seals, but also leading to potential carbonization of the fluid as it gets hot on the seal faces, as there is no cooling like a Plan 11 on the outboard seal. The introduction of an inert gas over the containment seal cavity, Plan 72, should be used to try and sweep any leakage from the cavity before it damages the containment seal. Plan 72 also prevents normal leakage of the process to atmosphere and offers a level of cooling to the outboard containment seal, like the Plan 11 does to the inboard seal. AESSEAL recommendation and accepted best practice is always to use a Plan 72 in conjunction with Plan 75. Frequently, AESSEAL have found that containment seals have been applied without the appropriate piping plan for the service, and as such, this offers no increased level of safety or emission containment any better than a single or tandem seal. Tune in next week for the next session where we review different containment seal designs.